Welcome to another deep dive. Are you ready to have your mind blown? Because today we're talking about quantum entanglement.
It's definitely one of the most bizarre and counterintuitive concepts in all of physics.
And we're going to break it all down for you today, using the Novier PBS YouTube video called Einstein's Quantum Riddle as our guide. So strap in and get ready for a wild ride.
It's a journey that takes us to the heart of what we know and maybe what we don't know about the nature of reality.
All right, so to kick things off, let's just make sure we're all on the same page here. When we talk about quantum entanglement, what are we even talking about?
Well, in a nutshell, it's the idea that two particles can be linked together in such a way that they share the same fate no matter how far apart they are.
Okay, so like if one particle spins up, the other one spins down, even if they're, light years away from each other.
Exactly. It's as if they're communicating instantaneously across vast distances, which, as you can imagine, has some pretty mind-blowing implications.
Yeah, that doesn't sound like our everyday experience out. I mean, if I throw a baseball here, it's not going to instantly affect another baseball on the other side of the world.
Right. That's because in our everyday macroscopic world, we're dealing with classical physics. But when you zoom into the subatomic realm, things get a whole lot weirder. The rules change, and that's where quantum mechanics comes into play.
Okay, so we're talking about a completely different set of rules governing the behavior of these tiny particles. And one of the key principles of quantum mechanics is this idea that particles don't exist in a definite state until they're observed.
Precisely. It's as if they exist in this fuzzy cloud of possibilities until we measure them, and then they snap into a particular state.
So until we look at them, they're kind of both here and there at the same time. The video uses this cool analogy of a soccer ball. To see the atoms in a soccer ball, you'd have to enlarge it to the size of the Earth to even be able to see them. That's how small we're talking.
It's a mind-boggling scale, and it really helps to put things in perspective. Now imagine the brightest minds in physics grappling with these ideas back in 1927. Yeah, the Solvay Conference, a gathering of like Einstein, Marie Curie, Niels Bohr, just some of the biggest names in science,
Yeah.
all in one room debating the very foundations of quantum mechanics.
It must have been quite the showdown, and as you might expect, not everyone was on board with these radical new ideas.
Especially Einstein, right? He famously had a problem with the probabilistic nature of quantum mechanics.
Oh, absolutely. He just couldn't accept the idea that the universe was fundamentally governed by chance. His famous question, does the moon exist if no one is looking at it, perfectly captures his skepticism.
He was basically saying, come on, guys, are you telling me that reality depends on whether or not we're looking at it? It just didn't sit well with him.
And that skepticism led him to search for a way to disprove or at least challenge quantum mechanics. And that's where this whole entanglement thing really gets going.
So he wasn't trying to prove entanglement, he was trying to disprove it.
Well, it's a bit more nuanced than that. He and his colleagues Podolsky and Rosen came up with a thought experiment, a way to test the completeness of quantum mechanics, what we now call the EPR paradox. Okay, let's break that down. What was this EPR paradox all about?
Essentially, they imagined two particles that were linked together in some way and then separated by a large distance. Their idea was that if you measure the property of one particle like its spin, you would instantly know the state of the other particle no matter how far apart they were.
Hold on, you're saying that by measuring one particle, you'd instantly know the state of the other, even if they're miles or even light years away. That sounds an awful lot like faster than light communication, which Einstein famously said was impossible.
Exactly. And that was the point of their argument. They believed that this spooky action at a distance, as Einstein called it, was evidence that quantum mechanics was incomplete, that there must be some hidden variables, some missing piece of the puzzle that would explain this seemingly impossible connection.
So they were trying to show that something else was going on, some underlying mechanism that preserved locality and avoided this spooky action.
Precisely. They thought there had to be a more sensible explanation, one that didn't require particles to be communicating faster than light.
It's like a game of quantum chess, with Einstein and his colleagues trying to outmaneuver the proponents of quantum mechanics. So how did this epic battle of ideas play out?
Well, it would take another few decades and a brilliant physicist named John Bell to really move this debate forward.
John Bell. Okay, tell me more about him. What was his role in all of this?
Well, Bell was fascinated by this whole entanglement debate, and he came up with a brilliant idea, a way to actually test whether Einstein or Bohr was right about the nature of reality.
So he devised an experiment to settle the score once and for all. That's pretty audacious.
It was a game changer.
Yep.
His theorem provided a way to experimentally distinguish between the predictions of quantum mechanics and those of a local hidden variable theory, which is what Einstein and his colleagues were proposing.
So this was the turning point where entanglement went from a theoretical curiosity to something that could be tested in the real world. What happened next?
Well, unfortunately, Bell's paper didn't exactly make a splash right away. It kind of sat there gathering dust for a few years until another physicist named John Clauser stumbled upon it.
John Clauser. This is where the story gets really interesting, right? Tell me about him and what he did.
Clauser was immediately intrigued by Bell's theorem, and he decided to put it to the test. And not only that, but he had to get creative. He didn't have a lot of funding, so he had to scavenge equipment and build his experiment on a shoestring budget.
Talk about a dedicated scientist. He was like a physics MacGyver, cobbling together an experiment that would change your understanding of the universe.
It's a testament to his ingenuity and perseverance. And what he and his colleague Stuart Friedman managed to achieve was nothing short of remarkable. They conducted the first Bell test experiment using pairs of entangled photons, tiny particles of light.
So they were actually able to create and measure these entangled particles and see if they behaved the way quantum mechanics predicted.
And the results were inlatus. They found that these entangled photons were indeed correlated in a way that couldn't be explained by any classical local theory. It was a major victory for quantum mechanics and a blow to Einstein's hopes for a more intuitive universe.
So they basically proved that this spooky action at a distance was real, that these particles were indeed connected in a way that defied our classical understanding of space and time.
Exactly. And as you might imagine, this sent shockwaves through the physics community. But it wasn't just physicists who were paying attention to this groundbreaking experiment.
Oh, I've heard about this. There was another group that got really interested in entanglement, a group that you might not expect.
That's right. A group of hippies who called themselves the Fundamental Physics Group.
Hippies, you're kidding, right?
Yeah.
What were they doing getting involved in cutting-edge physics?
They were drawn to the philosophical implications of quantum mechanics, and they saw entanglement as a potential bridge between Western science and Eastern mysticism.
So we've got hippies in hot tubs contemplating the mysteries of the universe. It sounds like entanglement was capturing the imagination of people from all walks of life.
It was a sign that this wasn't just some obscure scientific theory. It was something that touched on profound questions about the nature of reality and our place in the cosmos. And that's just the beginning.
Yeah, I'm already feeling my mind bending. And we're just getting started. This is why I love doing these deep dives. We start with something that seems totally out there, and then we end up uncovering a whole universe of fascinating ideas and connections.
It's a reminder that the universe is full of surprises, and that the more we learn, the more we realize how much we still don't know.
So true. But we've got to take a break for now. Don't go anywhere, though, because when we come back, we'll be exploring how this mind-blowing concept of entanglement is actually being used to create incredible new technologies.
From quantum computers to unhackable communication networks, the future is entangled, and it's going to be a wild ride. Buckle up.
Welcome back to the Deep Dive. We've been talking about this crazy concept of quantum entanglement, where two particles are linked no matter how far apart they are.
And as if that's not mind-blowing enough, it turns out that this entanglement thing isn't just some theoretical curiosity. It's actually leading to some incredible new technologies.
Okay, so we're going from the spooky to the practical. That's what I love about this stuff. What kind of technologies are we talking about?
Well, one of the most exciting areas is quantum computing. These are computers that harness the power of quantum mechanics, including entanglement, to perform calculations that would be impossible for even the most powerful classical computers.
Quantum computers.
Okay.
Okay, I've heard that term thrown around, but I have to admit it still sounds kind of like science fiction to me. How do these things actually work?
Well, it all starts with the qubit. It's like the quantum version of a bit, which is the basic unit of information in classical computing. A bit can be either a 0 or a 1, but a qubit can be both at the same time.
Both at the same time. How is that even possible? So it's like saying a light switch can be both on and off at the same time.
It's one of those quantum weirdness things we were talking about earlier. Remember superposition, where a particle can exist in multiple states at once? Well, that's what's happening with qubits. They can be in a superposition of 0 and 1, which gives quantum computers a massive advantage.
So instead of just crunching numbers one at a time like our regular computers, these quantum computers can explore all these possibilities simultaneously. That's where entanglement comes in, right? These qubits can be linked together so they can work together to solve problems.
Exactly. It's like having a team of superpowered calculators all working in sync. It allows quantum computers to tackle problems that would take classical computers millions or even billions of years to solve.
Okay, I'm starting to see the potential here, but give me some concrete examples. What kinds of real-world problems can these quantum computers solve?
One classic example is the traveling salesman problem. Imagine a salesman who needs to visit a bunch of different cities and find the shortest possible route.
Yeah, I can see how that would get complicated pretty quickly, especially as you add more cities.
Exactly. As the number of cities grows, the number of possible routes explodes exponentially. It becomes a computational nightmare for a classical computer. But a quantum computer, using entanglement and superposition, can essentially explore all those possible routes simultaneously and find the optimal solution much faster.
So it's like having a team of millions of salesmen all checking out different routes at the same time. That's insane. And this isn't just some theoretical possibility, right? People are actually building these quantum computers.
Absolutely. The field is moving incredibly fast, and there are already working quantum computers out there. The video highlights the work of Jianwei Pan and his team in China. They've built a quantum communication network that spans over 1,000 miles using fiber optic cables.
A quantum internet. That sounds straight out of a sci-fi movie. And this network is already up and running.
It is. Banks and data companies are already using it to transmit sensitive information because it's incredibly secure.
Secure? How does that work? Does entanglement make it unhackable?
Pretty much. Because of the way entanglement works, if someone tries to intercept the information, the act of measuring it would change the state of the particles, and both the sender and receiver would know that something was up.
So it's like a built-in alarm system. It's like trying to eavesdrop on a conversation and having the people talking instantly know that you're listening.
Exactly. It is pretty mind-blowing. And they're not stopping there. Jianwei Pan's team has also launched the world's first quantum communication satellite.
A quantum satellite.
Wow.
What's the advantage of having a satellite for this kind of communication?
Well, sending quantum signals through fiber optic cables can be tricky. There's always some signal loss, and the distance you can transmit them is limited. But in space, those limitations are much less of a problem. The satellite allows them to send entangled photons across vast distances, potentially creating a truly global quantum communication network.
So they're beaming down entangled particles from space to create an unhackable internet. It's like something out of Star Trek. This is all so incredible, but I have to ask, is there still any room for doubt about entanglement? Could there be some other explanation for these results that we haven't thought of yet?
That's a great question, and scientists are always looking for ways to test and refine their theories. But the evidence for entanglement is pretty overwhelming, and there's been a lot of effort to close any potential loopholes.
Like that cosmic bell test I read about. They used light from distant quasars to make sure there wasn't some hidden influence messing with the results.
Exactly. It's a testament to how far scientists are willing to go to test the boundaries of our understanding. And the results of the cosmic bell test were pretty conclusive. It confirmed what previous experiments had shown. Entanglement is real.
Okay, so entanglement is definitely real. It's not just a theory. It's a fundamental part of how the universe works. And it's having a profound impact not just on science, but on technology and our everyday lives.
It's a beautiful example of how scientific curiosity and a willingness to challenge our assumptions can lead to incredible breakthroughs. But we're not done yet. We've talked about the technology, but this deep dive is about more than just that. It's about understanding the nature of reality itself.
That's what I'm most curious about. What does entanglement tell us about the universe and our place in it?
That's a question that takes us beyond the realm of science and into the realm of philosophy. Get ready, because things are about to get even more mind-bending.
Welcome back to the deep dive. We've been on this incredible journey through the quantum realm, exploring the mysteries of entanglement.
And how it challenges our very understanding of the nature of reality.
Yeah, we've gone from these tiny particles that are linked across vast distances to unhackable communication networks beamed down from satellites. It's been a wild ride.
And now we're going to take it a step further and explore the philosophical implications of entanglement. What does it all mean for our understanding of the universe and our place in it?
That's what I'm really curious about. We've been talking about all this mind-blowing stuff, but what's the big picture takeaway?
Well, one of the most profound implications of entanglement is that it challenges our classical notion of locality, this idea that objects can only be influenced by their immediate surroundings.
So you're saying that our everyday experience of space and time where things are separate and distinct might not be the whole story.
Exactly. Entanglement suggests that there's a deeper level of interconnectedness that transcends our classical understanding of space and time.
So like those entangled particles that are linked even when they're light years apart, they're not communicating through space as we know it. It's like they're connected on some other level.
Precisely. It's as if there's a hidden dimension, a realm of interconnectedness that we're just beginning to glimpse.
Okay, so reality is a lot weirder than we thought, but where does this idea of a holographic universe come in? I heard about that, but I'm not sure I fully understand it.
Well, the holographic universe theory is a mind-boggling idea that suggests that our three-dimensional reality might actually be a projection from a two-dimensional surface.
Wait a minute. You're saying that everything we see and experience, the vastness of space, the flow of time, it's all just a hologram?
It's a radical idea, but it's one that's gaining traction among some physicists. The idea is that all the information about our universe is encoded on this distant two-dimensional surface, and that our three-dimensional reality is just a projection of that information.
So it's like those holograms you see on credit cards or stickers, where a three-dimensional image pops out from a flat surface? Except in this case, the whole universe is the hologram.
Exactly. It's
Yeah.
a way of reconciling quantum mechanics with Einstein's theory of general relativity, which have always been kind of at odds with each other.
Hmm.
And it's a way of explaining some of the weirdness of entanglement.
Okay, so entanglement is like the glue that holds this holographic universe together. It's the underlying connection that makes it all possible.
It's a fascinating way of looking at it, and it raises some profound questions about the nature of reality and our place in it.
Yeah, if everything is interconnected on this deeper level, what does that mean for us? Are we all just part of this cosmic hologram?
It's a question that takes us beyond the realm of science and into the realm of philosophy and spirituality. It challenges us to rethink our assumptions about who we are and how we relate to the universe.
It's both humbling and awe-inspiring. We started this deep dive with this weird concept of entanglement, and we've ended up talking about the nature of reality and the interconnectedness of everything.
It's a reminder that science is not just about cold, hard facts. It's about asking big questions, exploring the mysteries of the universe, and expanding our understanding of what it means to be human.
And it's a reminder that there's still so much we don't know. The universe is full of surprises, and I, for one, can't wait to see what other mind-blowing discoveries await us as we continue to explore the quantum realm.
It's a journey that's just beginning, and entanglement is our guide.
Well, that's all the time we have for today's deep dive, but I hope you're leaving with a sense of wonder and a thirst for more knowledge. Keep exploring, keep questioning, and keep diving deep into the mysteries of the universe. You never know what you might discover.